The second type of FRQ we're going to see are accumulation and rates FRQ. So before we go through two examples, let's do just an overview. So the first thing you need to recognize when we're talking about accumulation and rates is to understand the meaning of the derivative and the definite integral in context with the problem. So these are typically application questions where you have to kind of understand how we, like what the derivative means and what the definite integral means conceptually. And we'll go through and talk about specific examples with regard to that. Another important thing to recognize is that the rate of something is equal to the derivative. Okay, so the rate of change of something is equal to the derivative. And then the integral of the rate with respect to time is equal to the amount. Okay, so if I integrate the rate of snowfall over the course of 12 hours, the value of that integral is it's going to be the total amount of snow that's accumulated over the course of 12 hours. Okay, and then the last thing I want to talk about is these will typically involve in/out problems. And so what I mean by that is there's going to be two rates of change working in opposite directions. So typically you'll have to kind of compare two different rates and do something with those rates. All right, so let's do an example. So our first FRQ involves bananas. Very exciting. So let's say when a certain grocery store opens, there are 50 pounds of banana on a display table. Customers remove the bananas through the following function right here. Some complicated sine function. And then after the store opens for 3 hours, employees add bananas to that shelf through this function. Okay, so we have a rate out, that's f of t, and a rate in, which is g of t. F of t starts at t equals 0. G of t starts at t equals 3. Okay, so the first question is, how many pounds of bananas are removed from the display table during the first 2 hours the store is open? Okay, so if I want the amount of bananas that's removed, I want to find the integral from 0 to 2 of f of t. Okay, and so we want to find the integral of f of t, and this is something we're going to do on our calculator. So we're going to find the integral from 0 to 2 of 10 plus 0.8 t sine of t cubed over 10, over 100 dt. All right, so in your calculators, let's try and evaluate this. So we get 10 plus the integral. So it's math 9, integral from 0 to 2 of 10, the 10 plus here on the inside of the integral. And that will matter. So 10 plus 0.8x times sine of x cubed divided by 100. Okay, and the value of this rate, the integral of the rate, is going to give us the amount. So 20.051, and we're going to round to 3 decimals. So round to 3 decimals. So this integral is equal to 20.051 pounds. All right, now let's find the derivative of f at 7. Okay, we're going to go straight to our calculator, and we're going to evaluate the derivative of this same function that we just integrated at 7. So we're going to find the derivative of f of t at t equals 7. Okay, so to do that, we're going to go to math, and then number 8 instead of math 9. Plug our function in here for f of x. And we're going to evaluate the derivative after we plug in our function at 7. So at 7. So negative 8.120. So the value of the derivative here is negative 8.120. Okay, what does this mean in context with the problem? So this is talking about when t equals 7. So we're going to say after the store was open for 7 hours, t's in hours, the rate that the bananas are being removed is decreasing by, well, if we're saying it's decreasing, we don't need the negative. It's decreasing by 8.120, and the units are a little weird here. They're going to be pounds per hour squared. So that's the rate at which bananas, it's the value at which the rate is decreasing. All right, is the number, letter C, that's letter B. Letter C is asking us if the number of pounds of bananas on display is increasing or decreasing at t equals 5. So remember, after 3 hours, the employee is adding the bananas onto the shelf. And so we want to determine whether or not, by comparing the rate at which the bananas are being removed and the rate at which bananas are being added, whether or not the total number of bananas is increasing or decreasing. And to do that, all we're going to do is, it seems complicated, but all we're going to do is take the amount of banana, or the rate at which the bananas are being added at 5. So this is the rate being added. And we're going to subtract this with the rate at which the bananas are being removed. Rate being removed. And so we're going to plug 5 into this function here, and then plug 5 into this function here, and then compare the two values. Just to save a little bit of time, if you plug 5 into g of x, or g of t, we get 11.533 minus the value when we plug in 5 into f of t, which is 13.796. When we find the difference, we get negative 2.263. So because we have a negative value, we know that the number of pounds of bananas is decreasing. Because the rate at which they're being removed at t equals 5 is greater than the rate at which they are being added at t of 5, t equals 5. So if the rate at which the bananas are being removed is greater than the rate at which the bananas are being added, the total number of bananas will be decreasing. All right, let's wrap up this problem by determining how many bananas are on the display table at t equals 8. Okay, so this is going to be an amount question, so we're going from the rate to the amount. So we want the total number of bananas that are on display when t equals 8. Okay, to do this, let's start by determining how many bananas are initially on the shelf. And that is given to us up here. That's 50, so 50 pounds of bananas. We're going to evaluate this integral. Well, it will be an integral by starting with 50. So the amount, we'll say the amount at 8, t equals 8, is going to be the initial amount, 50. That's the initial amount plus the integral of the rate at which they're being added, which is g of t. And the time of this integral is going to be from 3 to 8, because the employees don't start adding the bananas until t equals 3. And so this is the total amount added. And we are going to subtract the total amount removed. And this one actually starts at 0 because the customers are taking the bananas off right when t equals 0. As from 0 to 8 of f of t dt. And so this is the total removed. So if I want the total amount of bananas, I start with the initial amount. I add to the initial amount the total amount that are added onto the shelf, and by integrating the rate g of t, and then I subtract the total amount that are removed by integrating f of t. Again, I'm going to save time. We're just going to plug this directly in the calculator. But if you plug it in correctly, which in itself can be a little tricky, you should get 23.347 pounds of bananas. Okay, let's wrap up this video by going through one more of these accumulation and rates questions. So FRQ number 2. And if you want to see the point allocation here, just to compare your answers, these are how the points are allocated. Remember, these are all out of 9 points. Okay, FRQ number 2. So this one is the rate at which people are entering an escalator, and that's given as a piecewise function here. So it's given this complicated function for t is between 0 and 300, and then if t is greater than 300, the amount of people entering is 0. So how many people enter the line for the escalator during the time interval 0 to 300? So very similar to the last question. If I want the rate if I want the total amount that are entering, I'm just going to integrate the rate. Okay. So letter A, I'll do that over here again. If R is equal to 44 times t over 100 cubed, 1 minus t over 300 raised to the 7th, then the total amount of people who have entered the line from t equals 0 to t equals 300 is going to be the integral of r of t. Okay, and all you're going to do is plug this in your calculator. You should get 270 people if you plug it in correctly. Whoops, 270 people. And so that's the answer for part A. Okay, and just to save time, I'm going to try and skip plugging some of these in the calculator. Letter B, during the time interval 0 to 300, there are always people in line for the escalator. How many people are in line at time t equals 300? So we know that the amount initially, this is sort of like the last question of FRQ1. We want the initial amount. We want the total amount that have entered the line, and then the total number who have exited the line. And that's going to come from this right here. So for letter B, the total number of people in the line is going to be the initial amount. So this is initial amount. Plus the integral from 0 to 300. 0 to 300 is already, actually let's write it like this. So the integral from 0 to 300 of r of t. And then if I want the total amount that have left the line from 0 to 300 seconds, I'm going to subtract 0.7 times the total number of seconds, which is 300. So this is the initial amount. This is the total who have entered. This is total who exited. Okay, now let's evaluate this. So this is 220 plus 270. 70% of 300, this is 210. And so 290 minus 210, that's 80 people. That's the total number of people who are left in line at t equals 300, which is going to segue into our next question, which wants us to determine how many, or the first time that there are no people in line for the escalator. So if you can imagine, from 0 to 300, there are people entering and exiting the escalator. At t equals 300, there are 80 people in line. After t equals 300, there are people leaving the line, but there's no one entering the line because of the second part of our piecewise function here. So there are 80 people. At t equals 300. And so I'm going to take the total number of people and subtract the rate at which they are leaving times t, set it equal to 0. And so this equation will tell us the time at which that total number of people, 80, decreases to 0. And so we're just going to solve this for t. So we get 80 equals 0.7 times t. T is equal to 80 over 0.7, and we end up with 114.286 seconds. All right, and that's the answer for part C. Okay, let's answer part B, and then the answer for part A. And let's end this video with the last question. Okay, a really common question you're going to see here is finding the absolute maximum or absolute minimum of some function given a rate in and a rate out. Okay? Okay, so we want to find the total number of people in line, the time at which that number is a minimum. Okay? So, if I want to find the minimum of a function, we need to check the endpoints and then the relative extrema, specifically the relative minimum. So for letter D here, what I would encourage you guys to do is we're going to make a table here. I'm going to make a table. And on the table, it's going to be t over here on the left, and then we'll call this the amount of people as a function of t on the right. The first thing we want to do is always check the endpoints, or evaluate the endpoints. we want to determine the number of people at 0 and the number of people at 300. Okay? Well, the number of people at 0 is just the initial amount. That is given to us over here, and so that is equal to 20. The number of people at 300, that was the number of people who were left after 300 seconds. We calculated that in letter B. That was 80 people. And so at 300, there are 80 people. To prove the absolute minimum, we need to find the relative minimum. Okay, so let's start by making a function that represents the number of people as a function of time t between 0 and 300. So the way this is going to work is, we'll call this p of t. It's going to be equal to 20 plus the integral from 0 to some arbitrary number t, where t is going to be between 0 and 300. R of, we actually have to switch the variables here, x, because we can't use t, because t is already being used up here. So we're going to call this, think of this as like a dummy variable, okay? But it's still the same function. That's a little tricky. Minus 0.7 times t. Okay, so this function right here is a function that gives you the amount of people as a function of time t that are in line for the escalator. If I want to find the relative minimum of this, I need to find the derivative of this function. So we're going to find the derivative of this. So let's take the derivative of each three terms. Derivative of 20 is 0, that goes away. The derivative of the second term using the fundamental theorem of calculus, part 2, the t will come down and replace the x here, and so this becomes r of t. When we take the derivative of the integral, the operations cancel each other out, and the derivative of 0.7t with respect to t is going to be 0.7, and we're going to set this equal to 0. Okay, so the question is, where does p prime of t go from negative to positive? Because if the derivative goes from a negative value to a positive value, then the original function will go from decreasing to increasing, indicating that we have a relative minimum. And so what I'm going to do is use our calculator here to determine where the function does that. So I'm going to change the windows here, and we're going to wrap up with this. So we're going to go from 0 to 300 because we're starting at 0 and going to 300 equals t. And then y, let's do negative 5 to 5. Okay. And then what I'm going to do here is let's plug in r of t, so 44, and hopefully the window is good for this. X divided by 100 raised to the third power. Raised to the third power times 1 minus x over 300 raised to the 7th power. And then we're going to subtract 0.7. Okay, here's our graph. Uh-oh. Here's our function here. And I plugged in something wrong into the graph. Maybe it's the window. Okay, I don't know what I plugged in wrong. I'm not going to restart this video. I'm just going to tell you what the answer is. What you're going to do is find where the derivative goes from negative to positive, or that graph goes from negative to positive, and t should equal 33.013. Okay, so that's our t-value here. And then to find the actual p-value, you're going to plug that into this equation here. So p of 33.013 is equal to 20 plus integral from 0 to 33.013 r of x dx minus 0.733.013. Okay, and we're going to compare this to the endpoints. If you plug that in, you get 3.803. And so this is less than 20 and 80, and so this is going to be our answer here. So the x value is 33.013. That's the time at which the function hits an absolute minimum, and then the actual minimum itself, the minimum number of people, is 3.8. So if you're in line for this escalator, you want to hop in line at 33.013 seconds because at that time the line is the smallest. Okay? If you are finished with this video, guys, move on to FRQ number 3. I think you're going to find it's very similar to the first two FRQs. And I will put in what the graph will look like into the OneNote. I just don't want to spend time fixing that on the calculator. Thanks for listening.